Okay, let's look at linear functions on a different sort of vector space. This is a vector space of polynomials. And we're going to look at polynomials of degree 2 or less. So that's quadratic polynomials with standard addition and scalar multiplication. And so notice there are three coefficients, three arbitrary coefficients. A0 times 1 plus A1 times x plus A2 times x squared. That actually means that this vector space is three-dimensional. We'll see more about that later. Now on this polynomial, we can take the derivative. Right? Derivative of 1 is 0. Derivative of x is 1. Derivative of x squared is 2x. So we can write the derivative as of an arbitrary element of this vector space by using the linearity property. Right? We're basically distributing the ddx, and we get a0 ddx1 plus a1 ddxx plus a2 ddxx squared. We just plug in the values that we obtained up here, and we get this expression. Okay, so we now know the derivative of any second-order polynomial from this expression. And in fact, you can represent this as a matrix, which we'll see later. Now we've been talking about specifying linear functions by specifying them on a set of vectors, and then taking linear combinations of those vectors gives us the we can take any linear combination of those vectors and find the linear function on that linear combination. And this is the idea of a basis. These three vectors are what you would call a basis, because any vector in this vector space can be expressed in terms of those three vectors. All right, so this basis is a very important contact. Basis is singular, bases is plural. Okay, here's another example. So you take the linear operator L of 1, 1 equals 2, 4. L of 1 minus 1 is 6, 8. Okay, now we know that L of any linear combination of these two can be obtained as linear combination of the two output vectors. Now in fact, I can write any vector in R2 as a linear combination of these two. How do I know that? Well, I can set this up as a 2 by 2 matrix problem. If I want to express xy as a linear combination of 1, 1 and 1 minus 1, I can write xy as a times 1, 1 plus b times 1 minus 1. And I can write this as a matrix equation. In this case, a and b are the unknowns, and we're treating x and y as the knowns. All right? So we can solve for a and b, and we can write xy as a linear combination of these two vectors, x plus y over 2 times 1, 1 plus x minus y over 2 times 1 minus 1. Okay. So we can calculate how L acts on any vector by first expressing the vector as a linear combination of these two vectors, and then applying the L to these two vectors individually. So let's see how that works. Right, L of xy, I write xy now as a linear combination of the two vectors 1, 1 and 1 minus 1. These are my two basis vectors, and I know what L does on those two basis vectors. Now I use the linearity property backwards. If I have L of a linear combination, I can take the linear combination of the L's. These L's are the ones that I know. That was how L was specified back up here, right? That was the original definition of L. L of 1, 1 is 2, 4. L of 1 minus 1 is 6, 8. I've just replaced the L with a corresponding output expression. And then I just do some arithmetic and I get this output. Okay. Now, I use these vectors 1, 1 and 1 minus 1. There are any number of choices I could make of two vectors and specifying L on those two vectors and being able to get L everywhere. Okay. So any pair of vectors that has this property is called a basis. In the same way, I can use triples of vectors in R3 to specify a linear function in R3. Now it turns out I need a triple. 2 is not enough. Now I can go even farther. If I think of this vector space, which is defined by the linear combination of these two vectors, I don't need to choose these two vectors in order to get this entire vector space. I could equally as well have chosen these two vectors, right? This second vector is just 2 times this one, and any linear combination of these two vectors can easily be expressed as a linear combination of these two. Just here I would take this C2 and divide by 2 and use that as my C2 here. So these two vectors here and these two vectors here specify the same vector space. You could say they're two different bases of the same vector space. Similarly, this one here, you can find that this vector is the same as this one. This vector here is 1 times the first plus 2 times the second. All right, so these two vectors can be expressed in terms of these two. Similarly, these two vectors can be expressed in terms of these two. This vector 0, 1, 1 is just 1/2 times this minus 1/2 times this, and you would get the answer. Okay. Now, one thing to notice here. Look at these two vectors here, 1, 1, 0, and 0, 1, 1. In fact, this 0, 1, 1 is not a multiple of 1, 1, 0. You cannot express this one in terms of this vector alone. This is what we call independent vectors. If we look at our two-dimensional examples, the same thing. 1, 1 is not a multiple of 1 minus 1. So they're what we call independent vectors. Now, if I chose here 1, 1, and 2, 2, I'd run into a problem because I can't express any vector in xy as a linear combination of 1, 1 and 2, 2. If I take any linear combination of 1, 1 and 2, 2, still the x and y component would be equal. So there's no way, for instance, I could get 1, 0 or 0, 1. Right? So 1, 1 and 2, 2 doesn't cut it. But these two do because they're not multiples of each other. Now, in general, if you have more than two vectors, you have to guarantee more than not being multiples of each other. But such a set of vectors would be called linearly independent. And we'll be talking about that more. All right. So when we talk about basis, we always want to choose linearly independent vectors, because if not, we could throw some of the vectors out and we wouldn't need such a big set. Right? So basis is a set of vectors in terms of which it's possible to uniquely express any other vector. And we'll be exploring that concept quite a bit in subsequent chapters. All right, so we have just an introduction in this chapter, but we'll see more about that in later chapters. Okay, that's it.